Hello everybody. This is the last lecture of our this current module where we are designing combination circuits. So in this particular lecture we will we will learn about a new technique or different technique of designing circuit. This technique is called as iterative circuits. So the beautiful nature of this particular technique is that we don't focus on entire design, but we focus on a one particular cell or one particular part of the design which would be replicated for n number of times to which would be replicated for n number of times for a complete design. So in our last couple of lectures also we have seen some utilization of this particular iterative design. So for example, in whenever we were doing a ripple carry adders, so this adder, one full adder, was actually an iterative circuit which was repeated again and again. Similarly, in our previous lecture also, in array multiplier, the adder design is also an iterative circuit which was repeated in 2 dimensions. Because it was repeated in 2 dimensions, so overall we were able to create a full n cross n multiplier. Now we will see this particular technique in a more methodological way in this particular lecture. So we will take a couple of more examples and we'll see it from the perspective of iterative design, that if we need to design an iterative circuit, what would be the characteristics or how we will design that iterative circuit. The first example I'm going to take is a comparator. So in a comparator we are taking two inputs, let's say A and B, and irrespective of the size. So but let's say for the matter of this lecture, let's say we say the size is n could be anything. Now when we compare two numbers A and B, there would be three outputs. G means greater than. If A is more than B, then G would be 1. If A is less than B, then L would be 1. If A and B both are equal, then E would be 1. So essentially there are three outputs, G, L and E. If it looks like that in this particular case at least one of them has to be 1. Either it would be greater or less than or equal to. So but still three different variables are used or three different outputs are used so that we can be clear that whether it is greater, less or equal. So how to design a comparator, this has been also an interesting topic. So one of the option which has been used by multiple people is if we use subtractor. So let's say we use our adder circuit, and B, we take 2's complement of B, so that means we are subtracting B from A. Now if we are subtracting B from A and we see what is the output of my adder. If output is do we care about output? Actually no, we only want to know what is the sign of the output. If the output is positive, that means A was bigger, so we can set G equal to 1. If the output turns out to be negative, that means B was bigger, so we can say L equal to 1. But if output is equal to 0, that means A and B both were equal, so we have to set E equal to 0. So in addition to doing subtraction, we also have to have another circuit which will see whether the output is 0 or not. So that means there would be other than having a subtractor, other than having using adder plus 2's complement, we also require to AND all the outputs. We have to OR all the outputs to make sure that the output is whether all the bits were 0 or not. So this is one particular way. If somehow in the circuit where we are using comparator, if in that circuit there is already an adder and that adder could be reused, then people try to use this particular type of comparator. So now because we are able to share that adder, then, or basically we can reutilize that particular adder for other purposes, then we use comparator. And for example, in our computer systems or a processor, only one of either addition would take place, or subtraction would take place, or comparison would take place. In that case, it is very common that we use this particular type of comparator. Okay, so what could be the other alternative way? So for other alternative way, we have to see that how do we used to compare two numbers when we were in elementary classes. So when we were in elementary classes, the way we used to see from we used to compare from left to right, and if the any particular bit in the left is 1 and corresponding bit in the second number is 0, so that means we used to declare that the first number is bigger, or whatever number has the first bit as 1 is the bigger one. Now if we try to translate this particular approach for a digital circuit, then we have to write a complete binary equation. So we have to, we can't leave it in between. So for example, if it is a n bit adder and let's say is 16, so even though we came to know that it is bigger at only at the first bit itself, but we still have to go through all the bits till 0, because in the worst case it could be anything, so because we don't know what the number would be. Okay, and our latency, as we have discussed in our previous classes, our latency or delay of total circuit depends on the worst case path. So the idea is that we have to finally write all the equations till like an to a0. So for example, I have written one equation for 4 bit. We will say that let's say let's remember that G would be 1 if A is bigger, B is smaller. So that means either A3 bit, the MSB A3 is 1 and B3 is 0, then G would be 1, or A3 and B3 both are same, that means XOR would be there, but A2 is 1, B2 is 0. Or A3, B3 are same, A2, B2 is same, but A1 is 1 and B1 is 0, or all the 3 bits are 1, same, sorry, and A0 is 1, B0 is 0. So this essentially takes care of all the conditions, and this would be the binary equation expression or binary function for G. Similarly, we have to find out the binary function for less than as well as equal to. So this approach, although is good, complete, but has one challenge, that as soon as my number of bits are changing, I have to redesign, I have to find out these equations again. So what would be better if we can find out an iterative design which we can repeat every time. So we say that for 1 bit we design this circuit, and that can keep on happening. So in iterative comparator design, what we'll do is we will let's say right now, actually we can do it from either way, right to left or left to right, but for an illustration what I'm doing right now is from a right to left, so basically from LSB to MSB side. So in LSB to MSB side, the ith block or basically ith comparator design would be something like this, that there would be some input. Basically it says that from 0th bit to ith bit, it has been found that 0th bit to ith bit, if I compare, then A is bigger than B if GI is 1. If EI is 1, that means from 0th bit to ith bit, it has been found that A equal to B. And Li equal to 1 means that from 0th bit to ith bit, it has been found that B is bigger than A, or in other words, A is lesser than B. So this also take into ith bit of A and ith bit of B as an input, and it generates an output which also include AI and BI other than the previous comparison. So this is an if we are able to create this kind of a circuit, that means then we can traverse from 0th bit to first bit, then second bit, and we can keep on comparing. So at the time of 0th bit we know that whether which one is good, and then at the result of first bit we will say that whether combination of 0 and 1 bit, which one is bigger, which one is smaller. So this comparison keep on happening till the end. Now if I want to find out how to write out find the output, so there could be multiple methods again. So one method could be I can write a complete truth table, and then find out in what cases gi plus 1 would be bigger or would be 1, otherwise in what cases it would be 0. There could be alternative method also. By logical reasoning we can find out what would be the value of gi plus 1. So from the logical reasoning I am trying to find out for you. So now my A would be bigger than B if it is if it was already bigger and A and B both are same, or it doesn't matter what was the previous gi value, but if ai is more than bi, then also gi plus 1 would be 1. So in other words we can say gi plus 1 would be 1 if ai is 1, bi is 0, or if gi is 1, that means it was greater than, my a was greater than b for I minus 1th bits, and my current bits ai and bi both are same. So that means either both are 1 or both are 0. Then we can say that this a is greater than b till ith bits. Okay. Similarly we can also find out for the equal bit. For equal bit it is more reasonable and easy to understand that if previously also it is equal and now also it is equal, so previously it has to be equal ei, and currently also ai and bi both should be same, either both should be 1 or both should be 0. And similarly for li plus 1, ai has to be 0, bi has to be 1, and previously li should be 1, and the current bit should be both ai and bi should be same. So this way if we try to by logical reasoning we can find out what are the equations for the outputs gi plus 1, ei plus 1, and li plus 1. Now using this particular block we can see that first we'll have a comparator 0. So in comparator 0 we'll have G0, E0 and L0 as an input, and A0 and B0 would be the input from the input side, and similarly there would be the first comparator, 0th comparator, first comparator, second comparator. So remember the output of my second comparator, this COMP2, depends on all the bits from 0 to 2, 0 to let's say A0 to A2 and B0 to B2. And then this particular output tells me that whether a is greater than b, whether a is equal to b, or a is less than b till this particular bit, till ith bit. So it's comp I, then that till ith bit, whether which one was bigger or which one is smaller. Okay, so similarly we can have the final output also. If for an n bit comparator, now n minus 1, a n minus 1 and b n minus 1 would be input, and also the result of the previous greater than and equal to would be the input. Now see, because this design is iterative, I need to design only the one particular cell or ith cell, and then I can keep on repeating itself. It doesn't matter what is the value of n could be 4, n could be 20, n could be 100. So the only thing is I have to reiterate or basically iterate that particular cell. In Verilog also it is interesting, it's easier because we have this generate statement where we can simply generate from 0 to n, and then all these blocks would be instantiated. So, and similarly if we design it for a layout, then also iterative designs are easier for placement, because you can wire them easily, and they could be interconnection is very less. So yes, then one yeah so one question which comes to our mind, that okay, so usually the input to comparator is A and B, but it looks like that this particular design has three more inputs, G0, E0 and L0. From where and what should be the value of G0, E0 and L0? So this we can call boundary condition. So otherwise these iterative cells would be similar for all the points, but for boundary points, sometime for nth point or sometime for 0th point, it may be slightly different. So here we clearly know that the input is A and B, so we have to find out what should be the value of G, E and L, so that my comparator 0 is correct. So in this particular case, we can say the one option is that we say that it is neither greater nor equal to nor less than. So essentially all of them are 0. Initially we said that one of them has to be G, one of them either G, E or L, one of them has to be 1, but now we are saying all of them are 0. So because it's an initial condition, it's a reset condition, that in initial, when we have not started comparing, it cannot be greater, it cannot be equal, it cannot be less. So if that is so, then we can also simplify our design of comparator 0. Either we can simply assign all of them as 0, or we can simplify our design of comp 0, comparator 0 or 0th instance of my comparator, by saying that G1, the output of this comparator, G1 is equal to A0 B dash B0 dash, and E1 equal to A0 B0 plus A0 dash A B0 dash, and less than L1 is equal to A0 dash and B0, which means that it depends just on the 0th bit. 0th bit of A and B doesn't depend on G, E and L. All of them are 0. So in other words, you see the previous conditions. So because this is 0, we can eliminate this part, and because this is 0, now ideally we could have eliminated everything, but we have seen that if this is 0, then it just depends on this has to be a separate condition where both of them are equal. Okay, so basically E1 we are assuming as 1, correct, and L for this we are simply keeping it 0, so that means this whole part get eliminated. So my condition was wrong here. So actually G and L both were 0, but E0 was actually 1. Okay, so the overall design is something like this. Now this was from right to left. Can we design it from left to right also? Actually, in case of comparator, we can do either way. So even if it is designed from left to right, then also it is possible to write these equations and create a comparator design which is iterative and which is comparing bits from left from left to right. But yeah, you can take it as an exercise and do it in your as your tutorial or a homework. Okay, so the next example we are going to take is parity generator and detector. So before explaining this particular problem, first let me tell you what is parity. Parity is usually one bit which help us in checking whether the sequence is correct or not. So how does it do? Basically, that's why it is there at both the end, generator end and detector end. So in generator end, your parity would be one bit would be generated, and at detector end again it is detected from the sequence. If the bit comes out to be same as whatever is the parity bit, then we say that yes, there is no error. And a single bit parity can detect one bit of error, or one, actually it can detect 1 bit of error. So there are two kind of parities. One is called even parity, another is odd parity. Even parity is 1 if the number of bits are 1, and odd parity is 1 if number of ones are actually odd. So now how these parity bits are useful. So if you remember, in our very first lecture we were talking about the advantages of digital design over analog design and other things. So at that time we said that digital design has one beautiful feature, that if by chance one of the bit get flipped from 0 to 1, then there are techniques which can help them recover, help them identify that there is an error. So parity is one of the technique which can be used to detect if there is an flip of one particular bit. So this single bit parity can detect if there is a flip of one bit. More sophisticated error correction code, error detection codes are there, which can also correct if some of the bits are wrong, and they can also find out if more than one bits have flipped or are wrong. Okay, so let's focus on this even parity. In this even parity, what we are doing is, if the number of bits are 1, then the output is 1. Now if I want to design a parity generator or a parity detector, what I can do is, I can think of a design where it's also an iterative design. It doesn't depend on how many number of inputs, how many bits are there in input, whether input vector is 8 bit long or 16 bit or 32 bit. I just need to replicate this single bit design parity generator at all the places. Now since we are saying that even parity is 1 if number of ones are even, so that means this pi would be 1 if the number of ones previous to this 0 to I minus 1, so a0 to ai minus 1, if all of them were even, then my output would be even if ai is 0. Similarly, if all of them were odd and this ai is 1, then I can say my final output would be 1. So in other words, I can say that if the previous parity was 0, was 1, and my current input is 0, then also my output is 1. Or if previous parity was 0 and current input is 1, then also I'll have this even parity. Okay, so now if I have this single bit design, now I can iterate. I can say that for 0th bit also I can say p0 and a0 is the input, and then for the first bit, and for let's say it's a 16 bit vector, then for 16 bit also a15 and p15 would be the input, and p16 is the final parity output. So all these p1, p2, p3 up to p15, they are all intermediate inputs and outputs, but my p16 is the final parity output. Now what about the boundary conditions? So in case of boundary condition, we have to say that the previous parity was we have to consider whether the number of bits were even or odd, because 0 is considered even in case of binary. So we have to say that the previous bit was 1, so basically previous parity p0 is 1, so that means my p1 is going to be a0 dash. Okay, so I'll repeat. So it happened because we consider 0 as a even number, so 0 would be, so that means p0 would be considered as a even number or even parity, and that's why p0 would become 1, because p0 is 1. So we can simplify this equation as a0 dash, and this will become 0, so we can remove this part. So in boundary condition, the first cell will become p1 equal to a0 dash, or alternatively what we can do is we can say the input parity is 1, and then we can use simple iterative design without any simplification to the boundary cell. Okay, so this is how a parity generator detector can also be designed using this iterative design.